All right, thank you for coming here today about this session around seamless mobile real-time communication with WebRTC. During this session, we're going to talk about WebRTC on how to use it in a mobile app. But before that, let me introduce myself. I'm a freelance. I'm based in Paris. I'm also a member of the Paris Android user group, and also very proud of being here today, first time talking in San Francisco. Why this talk? I had the opportunity to discover WebRTC during a freelance mission last year for a client in video games, and more specifically in cloud gaming. During this mission, I've been lucky enough to set up a Compose multi-platform project to deploy a cloud gaming solution, mostly a remote controller, based on WebRTC. So the idea was to create a controller on iOS, Android, and actually play with the controller to a cloud gaming solution inside the browser. So if you are playing with friends, you don't have to bring your own remote. So I was able to discover things that I will share during this session with you today. So of course, web real-time communication is a WebRTC. It's a technology that enables real-time communication capabilities directly inside the web browsers and mobile applications. Its development and adoption marked significant milestones in the evolution of web communication technologies. With WebRTC, peers can stream video, audio, or even arbitrary binary data. So that's great for cloud gaming, for example. Let's take a small step back and let's have, for a few minutes, a look on what's the story behind WebRTC. The concept of real-time communication in browsers without the need for plugins started gaining traction around 2009, 2010, and Google played a significant role in this period by acquiring Global IP Solution in May 2010. This company known for developing high-quality voice and video processing softwares. In May 2011, Google announced the WebRTC project and open sourced its key components. This move aimed to standardize the technology and also make it freely available to developers and browser vendors. Then the World Wide Web Consortium and the Internet Engineering Task Force began working on an API, so the API and the protocols, respectively. The W3C focused on the JavaScript APIs, while the IETF worked on the underlying protocols and data formats. 2012, Mozilla, Google started implementing WebRTC within their browsers, Firefox and Chrome. And this period marked the beginning of practical experimentations and usage of WebRTC in real-world applications. 2014, WebRTC gained traction in the industry with various startups and established companies that integrated in their product for video conferencing, file sharing, or real-time data exchange. 2015, this technology matured with improved stability and performance. Services like appears.in, now Whereby, and other video conferences tools showcase WebRTC's potential in consumer and enterprise applications. 2018, the W3C officially published the WebRTC 1.0 standard, marking a significant milestone in its development. By this time, the WebRTC had seen widespread adoption in various domains, including telehealth, online education, customer support, or social media. 2020 pandemic accelerated the adoption of WebRTC as the demand for remote communication tools skyrocketed. Platforms like Zoom, Google Meet, Microsoft Teams, and also new enterprise saw massive usage, and many of which actually leverage WebRTC for their web-based solutions. Okay, that was part of the history. To give more context, more context, sorry. How is WebRTC architecture? Let's dig a bit into the standard and the way things are working with WebRTC. Let's start with basic architecture with mesh. In mesh, all the participants are directly connected to all other participants. This solution has some advantages. It's easier to set up with a low operation cost, but it requires a huge, high bandwidth, and also it's not scalable. So in graph theory, it's the same for meetings with people in your team, if like 14 people in the team. In graph theory, a graph with each node is connected to every node, and it's called a complete graph. So in your team, you have to speak with everybody. For a complete graph with n nodes, the number of edge or connection can be calculated using this formula, n times n minus 1 divided by 2. So the more your team is, the more connection we will need. And it's also a problem in this mesh. The more connection or clients you will have, the more it requires bandwidth. So another solution is the multi-point conference unit. You still have clients, A, B, C, but you provide a server. And the server actually talks directly to the clients. So this solution requires high computational cost for decoding and also encoding the stream. It also brings, and that's a disadvantage, high latency, sorry. Oh. Yeah. It also brings high latency at large scale. The server can be considered as a point of failure and needs big bandwidth. How about WebRTC? So basically, we have a client, A, that creates an offer, and then it sends it to a signaling server. The signaling server relays it to client B. The client B receives the offer. Then the client B creates an answer and sends it to the signaling server. The signaling server will relay it to the client A. Client A receives the answer. After that, we have ICE candidate exchange. We'll talk about that after. And both clients can gather the ICE candidates. And the ICE candidates are sent to the signaling server and relayed to other peers. And then a peer connection is established, and client A can talk to client B directly. So we had, within this process of establishing WebRTC connection between two pairs, two major phases. The signaling phases, so it's the phase that involves the exchange of connection information necessary for peers to connect directly. It's like your identity card. And this phase is not handled by WebRTC standard. It requires an external signaling server or mechanism. Then the second phase is the peer-to-peer connection phase. And this phase involves actual establishment of the peer-to-peer connection, enabling media, video, audio, or just a data channel to create a flow directly between the peers. You might ask, what is ICE? So ICE is the technique that combines a stun on a turn server to discover and establish the best connection path between WebRTC clients. It's part of the standard. It enables real-time communication even in challenging network environments. What's the stun server? The stun is a protocol used to discover the public IP address and port of any client. What's the turn server? A turn server acts as an intermediary with direct peer-to-peer connection, and when they are not possible to connect due to restrictive network configurations, they relay media streams between the client, ensuring reliable communication. Don't worry about that. Most of the time we are using a Google turn server. So now the big picture. This is the architecture of WebRTC. So you can see that client A speaks to NAT to ask for IP address or Google turn server if it's requested. Also, it needs a signaling server, and then when all the setup is done, communication between the client A and client B is well established, and now you have peer-to-peer connection. So the WebRTC includes API for communicating with the ICE server, but the signaling component is not part of the standard. The WebRTC, it transmits data over UDP, so User Datagram Protocol. As you might know, UDP is connectionless, which means that there is no establishment of any formal connection before data transmission, and each UDP packet is independent and can be sent to the direction without any prior setup. It has a minimum overhead, and it does not provide flow control mechanism like TCP. So it does not manage error recovery or acknowledgement of received data. So the increased risk of data loss is quite high with WebRTC, but also fast. The signaling server. So as I said before, signaling server is not part of the standard, but why not writing our own signaling server? And we will see that it's not so hard to create one. It needs, in order to work, two peers to share how they should connect. Usually, creating a signaling server is used, or this is solved with an HTTP-based API, REST service, or any RPC mechanism. So in our case, we're going to use WebSockets. And basically, the application can relay the data from one client to another. Let's use Ktor. We are all Kotlin engineers here. Creating a web signaling server for WebRTC in Ktor just involves setting up a server that can handle the exchange of SDP, the session description protocol that we've seen, and the ICE candidate between peers. If you want to, who has tried Ktor in the room? Yeah, okay, cool. If for people who don't know Ktor, I wrote some articles how to set up or to start with Ktor. So it's a series, just basic API. The concept is how to write it as a client or design first, not a code first experience when you're designing API, and also how to write tests. And you will see that it's actually quite simple when we come from the Android world. Anyway, basic wizard, start.ktor.io. Let's enable this WebSocket plugin because we're going to need it. And then we set up the project, and this is part of my return of experience. Don't use just basic string, try to wrap everything into objects. So what I did is actually created a data class with a WS packet, then with an ID, and then the raw data, so you know what you are sending, and you will see that it can be helpful because of the flow of WebRTC. And within the WS message enum, just put some, this is ICE candidates, this is from the ICE server, this is an init state, SDP offer, SDP answer, or error state. After that, just create, so this is basic stuff when you establish WebSockets. Who are you? And also it makes sure that you're not sending, if two clients are connected to the WebSocket, they are not receiving what they are sending. So it helps to filter and send from A to B and not A to B and A. So this is quite simple, just atomic integer, and once you get it, you just increment it. Basic rule to create a session. So inside Ktor, it's just very straightforward. You just install the WebSocket, you put some configuration like the ping period to maintain the WebSocket opened, with the timeout, of course, the frame size, and also, since we are using serialization, you will need a content converter using JSON, so everything is part of Kotlin. Then, within this, let's get just a list of connection with the atomic, so we know the clients. And then we have this routing brackets, this scope, where you can design WebSocket on any endpoint. So in this case, I created just the WebSocket to /connect. After that, once someone registers, we just register it as a connection. Of course, it's going to need some try-catch because it can fail. And then you have several ways of doing it in Ktor. I put the most idiomatic way with the while true, but you can also get a flow, we'll see that later, to consume the flow, or directly use an iteration for loop. Anyway, so with the WS packet, you receive your WS packet, and then what you do is just you perform within the when, whatever you want. Or for example, in this case, when I receive an SDP offer, from all my connection, I'm just not going to send it to the one that sent it to me because it's pointless, but to all the other, I will send the WS packet data, so basically the offer from them. So that's the two things that are happening here. We don't want to send any data to the one that sent us something, and we're going to cheat a bit here because I send directly the data format from the packet for the slide after that. Sorry, it's in JavaScript, but it's just to show you how easy it is for web developers to set this up. So basically, you can see that there is a script within this HTML page. Is it next? Yeah. And then we just handle the data, handle the offer, handle the answer, handle the ICE candidates, and that's it, basically. You just get a remote peer connection on when you are on ICE candidates. So you can see here the RTC peer connection is the object that is already available because since it's part of the standards, if you're using Chrome or Firefox, then that's straightforward. And then that's it. So what I suggest for you is that let's run it and let's see with my stupid HTML page how it works smoothly. So in this case, we just here. Let's run it. All right. So it's just to show you some logs. And let's open my crazy page. So for network, it's better to display this. So basically on top it's going to be the client, and below it will be the pair connection. So of course it's my local host, and my signaling server is in my local host. So it's a bit weird like this, but if I start calling, you see below it's a bit not as good as the camera on top because everything works. And you can see behind, this is basically all the logs from my signaling server. So that's it. It just works like that, and it's quite good actually. It's quite pretty smooth. All right. So this is how we just create a basic signaling server. Let's go back to the presentation. So now we have our signaling server. Let's have a look on how to use it on Android. So you have probably heard of third-party SDKs that are allowing you to easily set up a video conference. So this is getstream.io. This is LiveKit. I think they are based in San Francisco, LiveKit, from whatever. Anyway, so Google is the maintainer of WebRTC, but LiveKit is hugely contributing to a fork, which is basically the WebRTC SDKs. And as you might see in the README, they are enabling more capabilities inside WebRTC. So they are actually actively maintaining WebRTC. And as Android developers, we could directly use libRTC to make it work on Android. So, do you remember my diagram, my previous diagram, when I explained everything that is happening? Okay, I cheated a bit, it's more complex than that. There is this creation of offer. Sorry if it's a little bit small. So there is how to set the local description step. You have to send the offer, you have to read the offer, you have to retrieve the offer. So it's a huge sequence diagram that goes from here. So this is the diagram I generated. As a return of experience, you have two ways of handling this. Whether you consider that once I start something, I want a callback. Once I get the callback, I need to do this, etc., etc. So it's asynchronous. What I suggest is don't do that. Otherwise, it's going to be hard, especially during the first phase that we have seen before. When you establish the answer and the offer, the second phase can happen whenever it wants. So basically, the client can send iServer while you are just waiting for the answer. So basically, it's very hard to manage. You'd use state. So in client-server communication, or state machine, mostly. This state machine or asynchronous call, there are two different paradigms for managing interaction or workflows. The state machine here is best suited for scenarios where the workflow is complex and involve multiple states and require also clean state transitions. So in my personal experience dealing with this peer connection object through WebRTC, a signaling server as well, and sometimes stuff that are coming from the server because it's business logic, depending on your app, it will be way easier to manage it with a big clear state machine. So this is kind of a classical Android architecture I would recommend. We have a WebSocket data source in charge of the communication to the signaling server. It open and close the connection to the signaling server. It can be used to maintain also the ping session with the server. And it can also be used to inject some specific commands from your signaling server. As I mentioned before, some business logic, like you have to do this, configure this client. So it can be useful to inject values from here. We will have the WebRTC data source. So it's in charge of the peer connection object from WebRTC. It will create and receive offer and answer. And also it will manage the ICE candidates and also negotiate the RTC configuration. Two data sources. We combine, literally combine, you will see, the flow from both data sources and produce a state that our app will use. Are you in pairing mode? Are you connected? What state are you? Are you in error? And then, of course, a view model on top. That is going to be used by your UI. You can inject events to produce new connection states, and retrieve some commands from a peer from the signaling server, for example. All right. Let's start with the WebSocket data source. We use Ktor server to build our signaling server. So why not using Ktor client with our Android app? So in this case, you will see that I put a ping job, and I'm kind of managing the ping myself because it does not work really well in Ktor server, in Ktor client. You might have experienced that. So manage your ping by yourself because sometimes the connection is closing and you don't know why. So I'm installing some logs, the WebSocket with the Kotlin WebSocket serialization converter, so I can use Kotlin X serialization directly. And then the part that is interesting, the WebSocket data source stream that is going to be consumed by my connection repository. Basically, we just receive messages. We'll see this method after, but on start, we just open the WebSocket session. Here, send message with the init is just to say, hey, I'm here. Let's connect. And the open is just basically set up the host, the path, the port, and also very useful, I put it here, WS, but use WSS as secure. It's easier. I mean, more better. And send messages. So just send some value. So it just send a WS packet, basically, not doing anything else. And the receive the messages. So this is something that I've noticed. This we have to emit the session with Ktor client. Otherwise, it's not really initialized yet. Well, they probably will fix that later. And before that, I mentioned that we were able to have the while true and also consume as flow. So with Ktor, you can just directly consume. So with this, I'm just deserializing all my WS packet and send them to my connection repository that is going to consume this flow of packets. And also, sorry, on completion, don't forget the cancellation exception to say that the WebSocket is terminated. Can be also used for your state machine. The WebRTC data source. First thing is that we will need a peer connection. You will see that there is a default RTC configuration. We'll see that after. I never managed to use something else because it works with the default one. We can also create a data channel. The data channel, as I said, there is audio, video, but for arbitrary binary data, we need to create a data channel. So let's create it inside the init directly. And also we have some peer connection callbacks, the on-ice candidates, the on-connection state change that are helpful for us to know which state we are. And we put that directly state inside the stateful. We can send the command, we can create an offer with a session description, we can create an answer. Everything inside is actually managed by the standard, so it's basically forwarding the good method to the signaling server. To create RTC configuration, again, iServer is an object part of the standard, so you just have to provide some URLs, some credential if needed, some username if needed. We have to close. And as I was mentioning with the Turn server, you can directly use the Stun server from Google. I think there is Twilio that, I don't know if they are still doing WebRTC because I've read something about that, but you still have also Stun server from Twilio if you want, maybe it's easier. All right, so now the connection repository. We need a coroutine scope, and then WebRTC data source, WebSocket data source, and some connection information. In my case, I was in need of this. And then that's it, basically. You will see that we have a controller state, call it whatever you want, but it's basically how we connect from one client to another. And we combine the WebRTC data source and the WebSocket. And this can be hard to see, like this big when, but when you combine WebSockets and WebRTC, then you have a lot of states, and I was mentioning before, if you try to work with callbacks, then you're screwed. So try to be like, okay, I'm in error state, I'm going to do that. My peer connection is, I've just received iServer, I'm decoding it, creating my servers, my RTC configuration. I'm setting it to the WebRTC data source and just send them. That's it. Same for my ICE candidates. Same for my WS SDP answer. And for each of them, you can see at the end of each block, I'm just providing a pairing state. So for me, if I'm still sending ICE candidates, it means that my pairing state is still connecting. So it's basically an extra layer to make sure that from your view model, it's easy to know in which state you are. Okay, so we're now connecting from the peer connection state. So in WebRTC point of view, we're connecting, so we can receive answer, ICE candidates. In any case, we're still connected. Connected, disconnection, failure also, and closed. So for that, just catch, and then on completion, I'm just closing the WebSocket connection. Last part, again, this is part of the standard. You just have to provide the good value, so it looks scary like this, but actually writing it is just passing the data. So with that, we have Android. How about multi-platform? So who has done? Yeah, okay, perfect. How about who has done multi-platform here? Yeah. Okay, so for those who don't know multi-platform, then this is just an extra thing, but you can see from Kotlin multi-platform, so we are whole Android engineers, so it means that we are whole writing Kotlin. And today I'm kind of pretty happy that we have this, because as I've seen before, we are able to write Ktor, so server, so we are actually able to do some backend stuff. And with multi-platform, we're also able to do iOS now, and also we can do some WASM, so WebAssembly or web. And the question is, how are we able to use this in a multi-platform project? Because we have seen that setting up a connection with WebRTC can be tricky, and okay, and this is the kind of part when I'm saying that, okay, do we want to do this for Android and iOS when we can actually bundle everything and make sure that we have actually a pairing state? So, Alex Shepiliev is doing a great job in bringing WebRTC for multi-platform. So it's an open source project. Since WebRTC is a standard, we can take the iOS SDK, the Android SDK, the WebRTC adapter from NPM for JavaScript. And since it's a standard, we know the profile of each method, so we can actually wrap everything within a Kotlin multi-platform library. This library has room for improvement or debugging at the moment, but it's just wrapping everything within one Kotlin multi-platform library. An example. We would like to live stream a video from iOS app, Android app. How is it going to work, for example, in Compose multi-platform? So we would expect a video. So for those who are not familiar with a multi-platform, when you don't know the implementation for a platform, you put method like with expect, and actually, depending on the platform, like for Android, for example, we'll have the actual, and with the implementation of the Android part or the iOS part of the WebAssembly part. So we will have this video stream track, part of the SDK, a modifier with Compose, and an audio track because it will be just video on audio for this. No data channel, it's just a video. So for Android, we don't have yet the surface view. So we will have, unfortunately, to use an Android view binding, so Android view here, with the factory of create, please, the surface view renderer, and then we will pass to this surface view renderer the scales, the aspect balance, the scale aspect fit, and the renderer. So for iOS, same video stream track, and since we have the WebRTC iOS SDK, we can use a simple UIKit view and use the RTC MTL video view. It's the same than the surface view renderer. And we just pass along the scale aspect fit and the modifier. And then that's it, actually, using this. So what I have here is a project for you. A simple project. And let's run it on iOS. I have an iOS device here. So this is my sample here. And same as I did for the web, I'm just going to start here. And I'm going to call me. If I don't have network, it's going to be fine. Oh, sorry. Seems it's not calling here. In any case, I will build the WebAssembly one. It's here. It's building. Here. Maybe I changed something. Sorry. Let's do this way. All right. It worked. And now let's. You can see it. And now you see it. So with that, it's a composed multi-platform project. And just the video that you stream, okay, see, if I do that, you will hear some noise because I'm actually redirecting also the audio. So in this case, you will hear it. And same as before, below, it's not the same quality because, of course, it's sharing within my network. Actually, here it's sharing with the local host, I mean the Wi-Fi here. That's why it was an airplane mode, sorry. In any case, so this is a composed multi-platform project. It just works like this. And with this library, we've wrapped the Web SDK, the WebRTC SDK of iOS, Android, and WASM. We bundled that into a multi-platform library, and then that's it. The same logic, and with the connection that I said before, with the connection repository, it's going to work. Okay. I never thought that I will give an iOS demo on an Android conference, just by the way, so just... I think it's way easier. If I was showing Android, you will like, okay. What's next? What's next? What you have seen so far is I speak client A, client B. All right, 2 people. How about we are like 20 in the room? How about 20 people within the room? So there is another pattern, what we call SFU. So basically, when there is a client A speaking to a client B, so before I was showing one arrow with bidirectional, but actually it's 2 arrows. So when you have a client C, here we have 6 connections, like in mesh, you remember? So more connection, more people you have, the more bandwidth we will need. How about we put the server like this, still the same thing, but now the server is actually filtering and sending the value. So if you see before, the peer A, so the client A, goes to the SFU, and then the SFU is in charge of relaying every stream to the peer B and peer C. Peer B go to SFU, peer A, peer C. So the SFU, it's like combining the mesh and actually the unit we had before. So with that, the SFU becomes a media server component capable of receiving multiple media streams and then deciding which of those media streams we should send to this client or to which participant. Its main use is in supporting groups call and live streaming broadcast scenarios. The SFU don't process the media, but rather routes it around. As such, they just consume considerably less CPU than the MCU alternative, not the Marvel Cinematic Universe, the one we've seen before, alternative. Their performance relies heavily on network throughout. All right, let's go a step further. The common technology that are going to be used while we are using SFU. The simulcast, it involves sending multiple video streams at different quality, bitrate, resolution, simultaneously from the single sender to the SFU. So the simulcast helps optimizing bandwidth usage. And also it improves the user experience. So basically when you are low on network, you see that it's very blurry. That's part of simulcast. The temporal scalability that involves encoding a video stream at different frame rate. So the base layer provides a low frame rate, while the additional layers provide higher frame rates. We can insert streams that allows developers to access and manipulate the media streams, like filters, for example. And we have protocol converters that sometimes you want to convert WebRTC to live stream, so route from the single init server and send it, for example, to YouTube or Twitch live stream. So this is achieved thanks to the selective forwarding unit. Okay, what's next? Why WebRTC company exists? As business increasingly prioritize effective online collaboration, the demand for reliable WebRTC company has skyrocketed, as I said before, during the pandemic. WebRTC offers some powerful foundations for real-time communication, but it has its limitation. And this is where WebRTC's company step in. Scalability and performance, so raw WebRTC requires significant development effort. We have seen the diagrams. For security and compliance, implementing robust security measures and adhering to data privacy regulation can be complex. So this is where the companies step in. Also, customization and user experience. I was mentioning filters, for example, that can be held to tailor the WebRTC experience for our user in terms of specific needs that can be time-consuming for us developers when we are doing video conference. And also, you have seen this, it's easier to use sometimes an SDK than implement all the logic here. So, use cases as well. So I was mentioning the technological part, but there is many companies that exist, and I've tried to put down a list of all the business capabilities that WebRTC is offering. So we have EdTech for virtual classrooms that are helpful, telehealth, like to give healthcare provider the ability to connect with patients in real time through secure and reliable live video. Did I mention that WebRTC is secure by design from the standard? So that's very helpful as well. For HR tech, for fitness, for social, of course, gaming, events, or even dating apps. So, as a conclusion, as we look to the future, the integration of AI and ML technology in WebRTC are set to revolutionize the user experience. With innovation like real-time language translations, noise suppressions, and AI-driven video enhancements, the possibilities are endless. So, I hope I have shown you today that as Kotlin developers, we have tools and capabilities to achieve incredible things across multiple platforms, whether it's WebAssembly, iOS, or backend, or Android, of course. Our skills, to my opinion, are more relevant than ever, and in the context of this rapidly evolving landscape within the AI. So thank you for hearing me.